A variable sweep wing, colloquially known as a swing wing, is an airplane wing, or set of wings, that may be swept back and then returned to its original position during flight. It allows the aircraft's shape to be modified in flight, and is therefore an example of a variable geometry aircraft. Typically, a swept wing is more suitable for high speeds, while an unswept wing is suitable for lower speeds, allowing the aircraft to carry more fuel and/or payload, as well as improving field performance. A variable sweep wing allows a pilot to select the correct wing configuration for the plane's intended speed. The variable sweep wing is most useful for those aircraft that are expected to function at both low and high speed, and for this reason it has been used primarily in military aircraft. A number of successful and experimental designs were introduced from the 1940s into the 1970s. However, the recent advances in flight control technology and structural materials have allowed designers to closely tailor the aerodynamics and structure of aircraft, removing the need for variable sweep angle to achieve the required performance. Instead, wings are given computer-controlled flaps on both leading and trailing edges that increase or decrease the camber chord of the wing automatically to adjust to the flight regime. This is another form of variable geometry, although it is not commonly called such. History. The 1931 Westland Hill Pterodactyl IV was a tailless design whose lightly swept wings could vary the sweep through a small angle during flight. This allowed longitudinal trim in the absence of a separate horizontal stabilizer. Later, experimental aircraft were built to study the effects of a simple swept wing. The first of these was the Messerschmitt P-1101, whose sweep angle could be changed on the ground. World War II in Europe ended before the P-1101 could be completed. Soon afterwards, the P-1101 was taken to the United States for study at Bell Aircraft, but because of missing documentation and structural damage, Bell decided against completing it. Instead, a close copy was constructed which featured wings that could adjust sweep angle in flight. One problem discovered while testing the Bell X-5 was that as the wing pivoted rearward, the lift vector also moved to the rear, pushing the nose down. A system to compensate for this basic effect had to be added for any such design to be viable. Immediately after the war, Barnes-Wallis had started work on variable geometry to maximize the economy of supersonic flight. Initial work was on the military Wild Goose project. Then he went on to the Vickers Swallow, intended to achieve a return flight from Europe to Australia in 10 hours. It had a blended wing tailless design, and he successfully tested several models, including a 6-foot scale model at speeds of up to Mach 2 in the 1950s, but government backing was withdrawn. Wallis and his team presented the work to the Americans seeking a grant to continue the studies, but none was forthcoming. In March 1949, the aeronautical engineer Elie Baines of Freyrs designed and patented a supersonic variable sweep wing fighter. He lodged patent applications in Britain and subsequently in May 1956 was granted a U.S. patent for high-speed aircraft wing and tail surfaces, having variable sweep back. In February 1951 he applied for another patent for a supersonic variable sweep wing and tail fighter. The design was built and wind tunnel tests were completed successfully, but due to budget constraints at the time, the design failed to receive government backing. A variable sweep wing was tried on the Grumman F-10F Jaguar in 1952. The XF-10F never entered service. It possessed extremely poor flying characteristics and rather vicious spin tendencies. The idea was again revived in the early 1960s as a way to reconcile ever-growing aircraft weights with the need to provide reasonable takeoff and landing performance. The United States adopted this configuration for the TFX program, which emerged as the General Dynamics F-111, the first production variable sweep-wing aircraft. Similar requirements in the Soviet Union also led SAGI, the Soviet Aerodynamics Bureau, to explore the possibilities of variable geometry. SAGI evolved two distinct designs, differing mainly in the distance between the wing pivots. A wider spacing not only reduced the negative aerodynamic effects of changing wing sweep, but also provided a larger fixed wing section which could be used for landing gear restores pylons. This could, in fact, be adapted to more or less existing airframes, which the Soviets soon did with the Sukhoi Su-17. The limitation of the wide spacing, however, was that it reduced the benefits of variable geometry as much as it reduced the technical difficulties. For the new, clean sheet Soviet designs, SAGI devised a more narrowly spaced arrangement similar to that of the F-111. This design was used for the MiG-23 fighter and the Sukhoi Su-24 interdictor, which flew in prototype forms at the end of the 1960s, entering service in the early 1970s. As of 2014, more than 100 Tupolev Tu-22M strategic bombers are in use. In the aftermath of the cancellation of the TSR-2, the British had started a project with the French for the Anglo-French variable geometry aircraft. When French commitment was curtailed, the British sought a second partner in the F-104 consortium of European nations. This in turn led to the European consortium that adopted variable geometry for the multi-role combat aircraft project that emerged as the Panavia Tornado. This was an interdictor and standoff interceptor similar in function to the F-111, albeit on a smaller scale. After AFVG, Dassault Aviation built a prototype fighter in 1968, Dassault Mirage G, two variants Mirage G4 and G8, and in cooperation with Lingtemco Vought, the LTVV 507 for VFX project. Meanwhile, the U.S. Navy introduced the Grumman F-14 Tomcat to replace the cancelled F-111B Fleet Interceptor with a fighter more nimble than the F-4 Phantom. Unlike the F-111, its variable sweep wings were programmed automatically by speed and could be swept under G-loading. In air combat, the wings could be swept forward for tight bat turns and back for dash speeds. Rockwell, meanwhile, adopted variable geometry for the Advanced Manned Strategic Bomber program that produced the B-1 Lancer bomber, intended to provide an optimum combination of high-speed cruising efficiency and fast, supersonic penetration speeds at extremely low level. The last variable sweep-wing military aircraft to date was the Soviet Tupolev Tu-160 Blackjack, which first flew in 1980. A variable sweep wing was also selected as the winning design used by Boeing's entry in the FAA's study for a supersonic transport, the 2707. However, it evolved through several configurations during the design stage, finally adding a canard, and it eventually became clear that the design would be so heavy that it would be lacking sufficient payload for the fuel needed. The design was later abandoned in favor of a more conventional tail delta wing. While variable sweep provides many advantages, particularly in takeoff distance, load carrying ability, and the fast, low-level penetration roll, the configuration imposes a considerable penalty in weight and complexity. The advent of relaxed stability flight control systems in the 1970s negated many of the disadvantages of a fixed platform. No new variable sweep wing aircraft have been built since the Tu-160, though it has been noted that the F-14's replacement, the FA-180, has a reduced payload range capability largely because of its small fixed wings. Variable sweep aircraft. Experimental Westland Hill Pterodactyl IV. Bell X-5. Dassault Mirage G Messerschmitt MP. 1101. Grumman XF-10 F1 Jaguar. Production General Dynamics F-111 Aardvark. Grumman F-14 Tomcat. Miko Jan Gurevich MiG-23. Miko Jan Gurevich MiG-27. Panavia Tornado. Rockwell B-1 Lancer. Sukhoi Su-17, 20 and AMP-22. Sukhoi Su-24. Tupolev Tu-22M.